Welcome back, students. Topic of today's lecture is output equation of three-phase induction motor. What is output equation? Output equation gives the relationship between the output of the machine with its main dimensions. In other words, it is the mathematical expression which gives the relation between the physical and electrical parameters. Physical parameters are like the dimensions of the different parts, and electrical parameters are like the kVA rating. Now, before starting with the derivation of output equation, let we discuss about the nomenclatures we are using within a derivation. EPH we are using for the EMF induced per phase in volts, IPH for the current per phase in ampere, TPH is the number of turns per phase, phi is the flux per pole, P is the number of poles, kW is winding factor, BAV is the average flux density, AC is the ampere conductor per meter. Now, like the DC machine, here in the induction motor also, the BAV is also called as the specific magnetic loading, and AC is also called as the specific electric loading. The capital D and capital L are the armature diameter and stator core length respectively, and these are the main dimensions of the machine. Small ns is used for the synchronous speed in RPS, whereas the capital Ns is used for the synchronous speed in RPM. Now let me discuss the output equation. The product EPH into IPH is the VA rating of the machine, and the multiplication with these three gives the total VA in the three phases. And here the 10 raised to minus 3 product converts this VA into the kVA. So the kVA equation of three-phase induction motor is 3 into EPH into IPH into 10 to the power minus 3. But we know that the EMF per phase by the EMF equation of three-phase induction motor is 4.44 kWf phi into TPH. Now, if we put this value of the EPH in the kVA equation, then the kVA equation becomes 3 into 4.44 kWf into phi into TPH into IPH into 10 to the power minus 3. Now we are writing this equation in the form of specific electric and specific magnetic loading. The specific magnetic loading is the ratio of the total flux to the area of the flux path. Now the total flux is the P phi and the area of the flux path is pi dl. So the BAV is equals to P phi divided by pi dl. And the specific electric loading is the total armature ampere conductor to the armature periphery. So in every turn there are two conductors, so the 2 into TPH is the total conductors in one turn, and if we multiply here is the with the IPH, then it gives us the total ampere conductors in one phase. And then if we multiply here by the 3, then this term gives us the total armature ampere conductors in all three phases, and the armature periphery is pi d. So the specific electric loading AC is the having this equation. Now also we know that the synchronous speed in revolutions per minute ns is equals to 120 f by p, and if we write this equation into the RPS, then we have to divide capital Ns by 60. So we will get here 60 is cut by the 120 and remaining is the 2. So the small ns becomes 2f divided by p over here. Therefore, from this equation of the ns, if we write the equation for the frequency, then the frequency becomes ns into p divided by 2. And also from the equation number 2, so from the equation number 2, If we write the equation of the phi, then the phi is equals to BAV into pi dl divided by P. And from the equation number 3, if we write the IPH into TPH product, then the AC into pi d divided by 3 into 2 is the equation for the IPH into TPH. Now we have the three equations with us: frequency, phi, and IPH and TPH. So these three equation values we will put in the equation number 1 here. So we have the phi F is equals to Ns into 2 divided by P. So F is equals to Ns into P divided by 2. Phi is equals to BAV into pi dl divided by P, and IPH into TPH is AC into pi d divided by 3 into 2. So if we put these three values in the equation 1, then the KVA equation becomes (3 into 4.44 into kW into Ns into P by 2 into BAV into pi dl divided by P into AC into pi d divided by 3 into 2 into 10 to the power minus 3. Now here you can see in this equation, this 2 gets cancels with this 4.4 and it becomes 2.22, and this 2 gets cancels with this 2.22 and it becomes 1.11. Also this P gets cancels with this P, and this 3 gets cancels with this 3. So what is the remaining part of the equation? 1.11 into BAV into pi is pi square, d into d is the d square, L into 10 to the power minus 3. So the KVA equation becomes 1.11 into kW into Ns into BAV into AC into pi square into d square into L into 10 to the power minus 3. In this equation, the d square L into Ns we taken outside, and remaining term we took in the bracket, and the term which we have taken in the bracket is called as output coefficient, and it is denoted by CO. So the value of the CO is 1.11 into kW into BAV into AC into pi square into 10 to the power minus 3. So if we take this, the KVA equation becomes CO into d square L into Ns. So the equation 8 here and equation number 9 is called as output equation of three-phase induction motor. Now the output equation of three-phase induction motor can be written also from the equation number 9, as the equation number 9 is KVA is equals to CO d square L into Ns. So from this equation we can write the d square L is equals to KVA divided by CO into Ns. Now the output equation can be written in the different way, like we can write the output equation like the equation number 8, equation number 9 and equation number 10. So all these three equations shows in the equation 8, 9, 10 are called as output equation of three-phase induction motor. So friends, I hope you understood this derivation, and thanks for watching.